last time we started probabilistic Turing machines and we defined many complexity classes like BPP, ZPP, RP, co-RP, right, depending on what the error is. All these classes are supposed to be or conjectured to be much below PP. Okay, although PP was also called probabilistic polynomial time, it's not really a practical complexity class. The practical ones are these that we are now studying. So, ZPP is RP intersection co-RP. It's in actually NP intersection co-NP, but so conjecture to be much easier, closer to P, and similar things for RP, co-RP and BPP. Now, the question is that we were trying to understand how important is this success probability of 2/3 or error probability of 1/3. Okay, and we claim that it's actually not very important as long as you are inverse polynomially away from half, or inverse polynomially success is more than half by inverse polynomial and error is less than half by inverse polynomial. Okay, so half plus 1 by n to the c. So, this is because of something called probability amplification. Okay, the theorem says that if a probabilistic Turing machine succeeds with an advantage of 1 over n to the c over half, then it actually can be amplified the success probability almost close to 1, and where close means actually inverse exponential close to 1. So, you can get up to 1 over 2 to the n close to 1. This is done by defining a Turing machine PTM m prime, which just repeats the Turing machine m k times. K is some polynomial in the input size x. So, it runs m k times with independent identically distributed strings and takes a majority vote of their output. Okay, think of k as odd. So, then there were odd many experiments, and what is the majority, right? Just more than k by 2. So, let us define an indicator variable xi. It is 0 if ith experiment is wrong, 1 if it is right. So, what is the chance that the sum of xi is less than k by 2? Okay, what is the chance that the majority is wrong? So, the correct answer appears less than k by 2. So, this is given by Chernoff bound. So, the Chernoff bound theorem says that if you have k random variables, independent, identically distributed, okay, so in short IID, Boolean random variables, with their probability of being 1 is p and 0 is 1 minus p for all the i's. Then for all delta fractions, proper fraction between 0 and 1, the probability that this average sum up x1 to xk, take the average. So, the average is also between 0 and 1. So it being away from P by an amount greater than delta. Okay, this happens with a small probability. That is what it says, Chernoff bound says. So it says that the probability is smaller than e raised to minus delta square pk by 4. So the chance that average of these k experiments is away from p. P is also the expectation, right? P is the expectation of this mean. This you can is also the expectation so the experiment giving you something delta away from the expectation, this probability is quite small. And if you look at this, so delta is some constant, p is some constant, 4 is a constant. This is actually growing as you increase k, it says it is falling exponentially. Okay, so we can actually write it like this to see the effect. Delta square pk by 4 delta square p by 4 and then minus k. Okay, so as you increase k, this fraction is falling. It is getting close to 0 exponentially fast. That is what Chernoff bound says. And this helps you in reducing the error probability exponentially close to 0. So this means that recall this definition of m prime. So this means that the probability that m prime is wrong which is the same as the probability that sigma xi is less than k by 2, which is the same as the probability that p minus sigma xi by k is greater than p minus half. Right, sigma xi by k less than k by 2, sigma xi by k less than half means that the difference from p is large. And what is in our application p? So in our application, in the theorem statement, p was just above half by an inverse polynomial. So let's invoke that. So that is the same as p minus sigma xi by k, absolute value being greater than n to the minus c. So the average from the expectation is away by n to the minus c. This probability is, by Chernoff bound, it is less than exponential in minus 1 by 4 n to the minus 2c, which is for delta square, and then we have a p and k. So p is half plus n to the minus c, and k we picked to be 8n d plus 2c. Okay, so this we get from Chernoff bound, and now let us just simplify this to minus n to the d (1 plus 2 n to the minus c), which is less than e raised to minus n to the d, which is less than 2 raised to right? So the error probability in the theorem claim, in the theorem, the statement claimed that error probability is 1 over 2 raised to n to the d, and that we have shown. Okay, so this is by Chernoff. So Chernoff bound immediately gives you the analysis for M prime, which is this we can also call probability amplification. Success probability is amplified above and error probability is amplified, is reduced all the way to 0, exponentially close to 0. I will not prove Chernoff bound here because that we do in probability courses. It has a really nice proof, elementary proof, which you can try as an exercise. So Chernoff bound has a neat proof using this operator of expectation on e raised to t times sigma xi. Okay, you look at not the sum of xi, but actually exponentiation of that. T is a variable, and use Markov bound. Okay, Markov bound is essentially the definition of expectation. It follows from that. So using this, using Markov bound and the expectation of e raised to some xi, sigma xi, you can deduce this this statement that we have written. Okay, so I will not do that here. And Chernoff bound has many other variants. Okay, in different situation, you can also relax this IID condition, and you can also make the random variables xi's non-Boolean. They start taking other values. So it is generally a very fundamental, important, useful bound in probability theory. So that shows BPP can be defined for any constant away from half, and notice that this n to the c is necessary. Okay, you cannot do this with PP. This half plus 1 by n to the c is necessary. You can't apply, you can't amplify PP algorithms. Or even half plus 2 raised to minus n to the c. Okay, so PP has only a guarantee of half success probability, and even if you have slightly more than that, half plus 2 raised to minus n to the c, that will not be enough. Okay, because then you have to take k very large, so you cannot really amplify PP or that kind of success probabilities which are very close to half, and the same thing on the error side. So you really need this polynomial, inverse polynomial separation. So to further understand the comparison, to compare BPP with PP, let's do the following. Let's see where So compare BPP with the polynomial hierarchy with PP, etc. Okay, is it contained there? Is it not contained? What do we know? So currently BPP contained in NP is not known. Is not known. But we will show that BPP is actually contained in sigma 2 intersection pi 2. Okay, so in particular BPP is contained in pH quite well. It is already contained in the second level, and in fact the intersection. It's an NP to the NP intersection co of that. And so it is much easier than PP, sharp P and those complexity classes. So we will be proving the following theorem. Theorem by Sipser and Gax. From 1983, they showed that BPP is in sigma 2. Once BPP is in sigma 2, you can also show that it's in pi 2 because you apply the co-operator. So BPP is in the intersection of sigma 2 and pi 2. So suffices to show that BPP is in sigma 2 because you will get BPP in co sigma 2. So BPP is in pi 2. The two are equivalent. So let L be a problem with a practical algorithm. So BPP, it is in BPP. There is a randomized polynomial time algorithm, and M be a poly time Turing machine. Let's say it uses random strings of length m, which is some polynomial in n to the c, such that for all x n bit strings, x is in L if and only if the probability over these random strings, random string R m bit, that m accepts x when run with this string. Okay, this probability is high. So this you can get by, I mean BPP only gives you 2/3 probability, but you can amplify and get probability very close to 1, and error probability 2 raised to minus n, right. So this you get by amplification. So this is the amplified success probability, and error is 2 raised to minus n. So that's what you are given. How do you show this in sigma 2? How do you show that L is in sigma 2? So here the idea will be that the number of R's is very large, which make M accept, and the number of R's which make it reject are few. So erroneous R's are very few. So we'll actually consider a graph on the space 0 1 to the m and do something with that. So let's consider the good x's. Consider in the yes input case, consider these good strings are in the space 0 1 to the m, such that m is forced to accept. So these are the good R's for yes. Strings and bad R's for no strings. Right. So for yes, you want the answer to be 1. So these are the good strings are, and for no strings you want the answer to be 0. So these are actually bad R's. The set size will actually drastically change for the yes. For the good, I mean when x is a yes string, S will be very large. When x is a no string, S will be very small. So what you get is S is at least this much if x is in L, and it is smaller if x is not in L. Okay, so there is a big difference between there is a big gap in the size of S, and idea is to check this difference in sigma 2. So check the largeness of this S in sigma 2. Okay, whether this set is large or small, we will try to solve in sigma 2. So use expansion properties of a graph on the vertices 0 1 to the m. Okay, whether this, so we will actually define a graph on 0 1 to the m. This is the space of random strings, and based on the behavior of m, we will draw edges here, and depending on whether x is yes or no, this graph will have different expansion properties or connectivity. So for u, k vertices, define this graph GU with vertices, as I said, 0 1 to the m, and edges. So what are the edges? That's trickier. So the edges will basically be if from a vertex somehow u1 can take you to another vertex using bitwise addition. Okay, so u1, this set u will guide you where to go from a vertex. So edges s comma s prime, if there exists an I such that s plus ui is s prime. Okay, so take one of the elements of the set u, one of the point, and using that point go to a neighbor of s. Okay, that's how the using bitwise or bitwise addition mod 2 or this XOR. So that's how you have the connectivity in this graph GU. So the first property to note is that GU is a regular graph with every vertex of degree k, right. So from S there are k directions you can go to using U1 to UK respectively. So that makes GU a regular graph. Let us now specialize this. What are the parameters? Or in fact, for any set S define gamma US to be the neighbors of S in GU. So for any subset of vertices, we can define gamma u to be the neighbors, right? So from vertices in S, which vertices can you visit by an edge? Okay, in one jump, where can you reach? That's gamma US. Yeah, and let us fix the parameter k to be m by n. Okay, so that's m and n were given to you, so vertices were fixed, and how big the set U will be, that we'll just take it to be m by n. Okay. Now let us see what happens in this graph GU if we take a set S small versus if we take a large set S. So claim 1 is what happens when S is small. So if S is less than equal to 2 raised to m minus n, then no matter what U is, neighbors are few. For all U of size k, gamma US is small. Okay, so this is the important point, that no matter how you pick k points in the set U, the graph GU, the way it is defined, neighbors of a small set cannot be everything, right? The number of vertices is 2 raised to m, it cannot be everything. Some vertex will always be outside the neighborhood. And claim 2 will be what happens when S is large? So if S is larger than 1 minus 2 raised to minus n, okay, if S is so large, very close to 2 raised to m, then there exists a U of size k such that gamma U S is everything. Okay, so this is how the size of the set tells you about its this expansion property of GU. Okay, so no matter how you define GU, define GU, what U is, if S is small, then from S you cannot reach all the whole space, all the vertices of GU. But if S is very large, then there will be a definition of GU where the connectivity will be so good that from S you can reach everywhere. Okay, and this is the difference which you can see that there is this, we have reduced it to quantification, right, for all versus they exist. So once we prove both these claims, it will be almost obvious that L can be written in there exists for all quantification. But let us first prove these claims. So these claims are to do with probabilistic arguments. At least claim 2 is. Claim 1 is almost direct. It's proof of claim 1. So we have reduced size of S to connectivity. In GU. So what is the size of gamma U S? So S has size of S many elements obviously, and each has at most k neighbors because size of U is k, right? So which is k times 2 raised to m minus n. That's what you are given. And so this is k by 2 raised to n times 2 raised to m. And what have we taken k to be? K is just m by n, right? So it's much smaller than 1. So it is definitely smaller than 2 raised to m. Okay, that is claim 1.